Hi there, my name is Lee from the University of Toronto, and this is Learning Matchable Image Transformations for Long-Term Metric Visual Localization, presented virtually for ICRA 2020. This paper is about metric visual localization, where the goal is to use vision to estimate the 6 degree of freedom pose of a robot relative to a visual map. If we want to localize continuously against a map over a long period of time, we need techniques for coping with appearance change, whether it's caused by relatively short-term changes like lighting and weather, or by longer-term changes like seasonal variation. Currently, the best tools we have for dealing with long-term appearance change rely on collecting multiple experiences or maps of the environment and storing them in a searchable data structure like a spatiotemporal pose graph. The idea behind this multi-experience localization approach is that if we can localize directly against one experience in the graph, then we can either use that experience as a map or else trace a chain of relative transformations through one or more intermediate bridging experiences to localize against a privileged mapping experience. While this approach is robust enough to handle a wide variety of appearance changes and accurate enough to use inside of a control loop for long-term autonomous route following, it does require us to acquire, store, and search a very large number of experiences, and keeping the localization pipeline computationally tractable requires strategies for identifying a handful of good experiences to use. An ideal visual localization system would be able to localize directly against the map without requiring any intermediate bridging experiences, and would be able to do so in a way that retains the key strengths of multi-experience localization, but with significantly reduced data requirements for online localization. There are a number of approaches in the literature that focus on making single experience localization more robust to appearance change by making the data association problem more tractable. Analytical image transformations, such as the image gradient or physics-based color constant transformations, can be used to transform images into a representation that is invariant to certain kinds of appearance change while still being useful for metric localization. These analytical transformations are cheap to compute, but are often limited to a small range of appearance conditions. Other work has focused on deep image-to-image translation as a means of transforming images from one appearance condition to another. Given enough of the right kind of training data, these approaches can be applied to a broad range of appearance conditions. However, they are often categorical in nature and not easily adaptable to the kinds of continuous appearance change encountered in long-term robotics applications. Still, other work is focused on learning local feature descriptors that are consistent under appearance change. These have the advantage of being sensitive to the image context, but often require large training sets of true and false point correspondences, which are expensive to obtain. While all of these approaches have different advantages and disadvantages, one thing they have in common is that they are not tied to any particular localization pipeline and make no guarantees that they will ultimately improve the performance of any given localization system. In this paper, we try to resolve this shortcoming by searching for an image transformation that explicitly optimizes localization quality for a given image pair and a given localization pipeline. That is, we want to find an invariant representation of the environment that is simultaneously sensitive to scene context, robust to appearance change, and guaranteed to be useful for 6 degree of freedom metric localization, and which we can use as a straightforward preprocessing step in a conventional visual localization pipeline. So our goal then is to learn good images for cross-appearance localization. And ideally what we would like is to have some flexible generator model that transforms pairs of images corresponding roughly to the same physical place, such that the performance of our target localization pipeline is maximized. This generator model could be a parameterized analytical transformation, a neural network, a combination of these, or some other type of model altogether. To train this model, we want to use the localization pipeline itself to define a loss function, and then backpropagate this loss function to train the generator using gradient descent. For example, we may want to minimize estimation error relative to ground truth, maximize the number of inlier feature matches, or optimize some other criterion that tells us about the performance of the estimator. The trouble is that conventional localization pipelines are not straightforwardly differentiable, so we can't use tools like backpropagation and gradient descent to train the generator like we normally would do in a deep learning context. But we can get around this difficulty by training a deep network to act as a differentiable surrogate or proxy to the localization pipeline and predict something like the number of inlier feature matches that would be detected for a given image pair. Once we've trained that network, it then defines something like a gradient direction in image space that we can move along to change the number of inlier feature matches for a given image pair. Surrogate methods like this are common in the numerical optimization literature for dealing with expensive or non-differentiable cost functions, and you can find examples of neural network surrogates in a variety of other fields, including computer graphics and computational oceanography. Now, if we attach our matcher proxy network to our generator model, we can set up a fully differentiable version of our problem where the loss function is defined by proxy and backpropagate something like a maximization criterion all the way through the model to train the generator using gradient descent. The next question to answer is, what should the generator look like? In this work, we looked at learning a pixel-wise mapping from RGB to grayscale color spaces that would produce the most matchable grayscale versions of a candidate image pair. This makes sense for two reasons. One is that converting RGB to grayscale images is already a necessary pre-processing step for using color cameras with conventional feature matchers, since they typically operate on single-channel images. And the other is that color constancy theory tells us that if we make some assumptions about the imaging sensor and the light source, we can derive an RGB to grayscale transformation that is resistant to lighting and can be expressed as a weighted sum of the log responses of each color channel. The key is knowing how to set the weights for each channel, and in practice the choice of weights depends on the specific materials in the environments and the specific camera. Instead of tuning these weights manually, we attached and trained a pairwise encoder network that would tell us the best weights to use for a specific image pair to maximize the number of feature matches. In this paper, we also asked whether a weighted sum of log responses was the best we could do, and looked at learning a bespoke nonlinear RGB to grayscale mapping, which we parametrized as a multi-layer perceptron. But just like with the color constant sum of logs transform, the best mapping might depend on the specific image pair, so we also compared learning a single one-size-fits-all transformation versus combining an MLP transformation with a pairwise encoder network to incorporate information about the scene context. We evaluated our approach on several different datasets with appearance changes originating primarily from lighting and weather, using a standard feature-based localization pipeline based on libviz02 feature matching and nonlinear optimization. We found that our proxy network can achieve very good test time predictions of the number of inlier feature matches after a few epochs of training, and that these predictions do a good job of accounting for both viewpoint changes and appearance changes between candidate image pairs. Here are some results from final trained models on the Virtual KITTI dataset. From top to bottom, we've shown the input RGB images, the standard grayscale transformation, the one-size-fits-all sum of logs transformation, the sum of logs transformation with a pairwise encoder network denoted by a capital E, the one-size-fits-all multi-layer perceptron model, and the MLP combined with a pairwise encoder network. You can see qualitatively that the appearance of the standard gray images is quite inconsistent, while the other four transformations give us images that are very consistent and which automatically get nice properties like removing shadows and increasing the contrast in regions of high texture. This comes purely as a consequence of maximizing the response of the matcher proxy network. In the plot on the right, we've shown the distribution of actual inlier matches for each transformation, and you can see that the number of matches is more than tripled using any of these transformations. The encoder doesn't make much of a difference in this case, and that's most likely because this dataset is relatively small and tends to have similar types of materials and objects in the scene, so a one-size-fits-all approach can be expected to do well. We also looked at the UTIAS In The Dark dataset, which is a much harder matching task since the dataset spans multiple traverses over a 30-hour period. Here we've shown the most challenging sequence where we're trying to directly localize across very different lighting conditions with no bridging experiences at all. We can see from the video that the standard grayscale transformation does not consistently produce many feature matches, but that the other transformations do a much better job. This is reflected in the distributions of match counts in the bottom left plot, where we can see that all four transformations significantly increase the average number of inlier matches, and that the extra pairwise encoder network gives a small performance boost relative to the one-size-fits-all approach. To measure localization performance, we examined the maximum distance traveled on dead reckoning between successful localizations, given some criteria for considering a localization attempt successful. In the bottom right, we've shown the maximum dead reckoning distances based on a fairly conservative threshold of 20 inlier feature matches against the map, and we can see that using the standard grayscale images, we would need to travel nearly 50 meters on dead reckoning, which is about 20% of the route, whereas with the other methods, we would need to travel less than 10 meters on dead reckoning. In particular, the SumLog-E method gets us all the way down to 3 meters, which means that if we have the right kind of training data, we can localize almost continuously across an entire day-night cycle with a single mapping experience and a relatively straightforward image preprocessing step. In follow-up work, we pushed this idea further and looked at how well we could account for seasonal changes using this method on the UTIAS Multi-Season dataset, which consists of a mapping sequence collected in the winter, followed by more than 100 traverses spanning all the way to spring. Here we have an extremely challenging localization problem where not only has the lighting changed, but the snow cover and weather conditions have changed as well. This is a case where the encoder network makes a big difference, as you can see in the match count distributions on the bottom left, since the one-size-fits-all models used up most of their model capacity handling other appearance conditions in the dataset. Looking again at the maximum distances traveled on dead reckoning, we can see that the SumLog-E method yields a big improvement, and that the maximum distance we would have to travel without localizing is just under 13 meters. In conclusion, we've demonstrated that learned pixel-wise color space mappings can significantly improve the performance of conventional metric localization pipelines across severe appearance change, and represent an interesting and viable approach to minimizing the number of bridging experiences needed to localize reliably across a variety of appearance conditions. To learn more about this work, please consult our paper in Robotics and Automation Letters. Finally, thank you to all of my co-authors and colleagues, to the organizers for facilitating a virtual conference, and to you for watching this video.